Here's an example like the problem we did in class with slightly more complicated because the velocity function here is a cubic polynomial, and the one we did in class, the velocity function was a quadratic polynomial. Here, instead of having someone running, we have a more abstract problem with a particle moving along an axis, or it's moving just left and right. And its velocity function at any time between 0 and 8 is given by this polynomial. So just like we did with the running problem, we really want to try to break down the journey of this thing in more detail. So in other words, we want to try to tell a story, like what is it doing? Is it going left, then left, or right, left, right? So however it's moving, let's see if we can break it down more. And that's really what the first question is asking, is when is it going left, when is it going right? And all of those things are going to be relevant to part C. So let's go ahead and do that. So the A part. In order to figure out when the velocity is positive and negative, it's just that sign chart idea that you had from Calculus 1. So we need to take our velocity function in the problem and first of all figure out where the velocity is 0, because we know that the only way that this polynomial can change from negative to positive or positive to negative is if it has to be 0 at some point. So finding out where the velocity is 0 is going to tell you the potential places where the velocity might be changing from positive to negative or negative to positive. Anyway, so we solve this polynomial. This factors. You could put it in a computer or whatever, but it does factor. So this is t times t minus 6 times t minus 4. And so I can see the values of t for which this is 0. I only care here, or realize, about values between 0 and 8. That's the only part of this that they're going to be using. And so the only values of t that are relevant to me are t equals 0, t equals 4, t equals 6, and t equals 8. And the 0 and 8 aren't really, we don't really have to check anything there. That's the beginning and end of the particle's trip. So the way we did this in Calc 1 was you do a sign chart, you put 0 on there, you put 8 on there, and you put 4 and 6. And then you sort of sampled values in between these numbers and plug them into your velocity function. So the velocity, so for example, if you look at the velocity at 2 is between 0 and 4, and you generally want to use the factored form. This is v of t right here as well. This is sort of a pain to use, but this is obvious to use. So if you put 2 in here, then that's positive, that's negative, and that's negative. So your velocity is going to be positive at 2. Then you plug in a number that's in the next range, so between 4 and 6. We do the same kind of game, put 5 in, and we have positive times positive, so that's a negative value. And then you'd plug in something like 7, that's in the next range, and you would get a positive value. So, so the velocity graph should be above the horizontal axis, should be above the axis between 0 and 4, below from 4 to 6, and above again from 6 to 8, and that's this guy d. All right, so now we have an idea of what this journey looks like. The particle is going in the positive direction from t equals 0 to t equals 4. Then it's backtracking a little bit between t equals 4 and t equals 6, and then it's going to the positive direction again from 6 to 8. So part B is asking about the displacement. Remember, displacement is just a way, in terms of position, to talk about where you end up relative to where you started. So this is just how far from the particle's beginning place it ends up at the end. And that's exactly what the integral is going to measure. So the integral from 0 to 8 of the velocity function is going to be the displacement. I'll go ahead and write down the antiderivative here for those of you still reviewing that stuff. So that's the antiderivative of the polynomial evaluated from 0 to 8. I'm not going to do that. Your problem will probably have slightly different numbers anyway, but But to do that, we would plug 8 into that antiderivative and then plug 0 into that antiderivative and subtract. And that'll give us a numerical value. And that is, the units for that is going to be meters. We know that because we're told that the velocity is measured in meters per second and the time t is in seconds. They don't actually say that time t is in seconds, do they? Well, that's what it would make sense for it to be, so that's what we'll go with. For those of you in science land, the unit analysis always makes sense here. If this is meters per second and time is in seconds, then that dt times the velocity is a measurement in meters. Meters per second times seconds is meters. So what you're doing there is you're doing a calculation that inside the integration has the units meters, and then you're summing up. The S is just summing up those measurements. So you can tell in the integration what the units are going to be by understanding the units of your velocity function and your t. All right, so then the total distance traveled is the only tricky thing. And for that, we really want to just break the journey up into the parts that we determined in part A. So if I integrate from 0 to 4, now the reason I'm doing 0 to 4 is because if I look up at my sign chart, the velocity is positive for that whole time. So my journey starts off in the positive direction, and the distance that it travels in the positive direction is just this integral. So this really is distance, not just displacement, because the particle never changes its direction. So its displacement from 0 to 4 is the distance that it travels from 0 to 4. I wouldn't know that if I didn't know from A that the velocity was all the same sign, was positive for that whole time. And then the same thing is going to be true, I'll just say here, your integral from 6 to 8 has the same issue. It's also going to give you the distance, the positive distance from 6 to 8, because velocity is positive. So that will be a distance that you're traveling in the positive direction. The one that's weird is the one that's negative. If I integrate 4 to 6 dt, well, the particle does not change direction during that time. So if you're measuring the integral from 4 to 6, and you know that the direction is negative for that whole time, then you're going to get a negative number, but that negative number is the negative of the distance. Your displacement is all in the negative direction, and so whatever the magnitude of that number is how far you went. So what we would do is just put absolute value bars around this. We know that that integral is going to come out to be a negative value, but I want to add it in as a positive distance. So the idea is that we're going to figure out the distance traveled in each of these three parts of the trip, from 0 to 4, 4 to 6, and 6 to 8. Each time that the integral involved is a positive number, then that really is measuring our positive distance. Anytime that's a negative number, I'd want to just take its magnitude to tell me how far that is. And then that way, I'm not letting the negative direction offset the positive direction. Overall, what you're really doing when you're doing that is just integrating the absolute value of the velocity function. But we don't have any particular integration rules for the absolute value function, so the only way we ever can deal with that is by breaking it up into pieces anyway. So all you're doing here is just sort of trying to apply the logic of the motion to the process rather than just make it a formal absolute value statement. Anyway, so just think about the distance in each direction, make them all positive, add them together. That's your total distance traveled.